Everyone, let's do a few examples about solids and fluids. Let's start with this one. A steel cable with a mass density of 7,800 kilograms per meter cube has a breaking stress of 1 gigapascal. How long of a cable can be suspended from the top of a building before it breaks? So the vision here is that we have a ceiling and we just stretch a cable down from it. It has some cross-sectional area that I don't know. It has some length that I want to find out, and it's going to then pull down on it until it breaks. And so the longer the cable gets, the higher the stress is, and the stress is going to be highest up here at the top. So we're really considering at this point. And at that point, below that, there's going to be a force pulling downward that's equal to the weight. So the force perpendicular, which is going to be in the stress, is just going to be the weight of the cable, and then the stress is F perpendicular over A, which is the stress, and the mass of the cable is just the volume, so it's going to be rho times V times G over the area, and then the volume of the cable is just rho times the area times the length times G all over the area. So those will cancel out. And then we have the answer is right here, because we're going to set that equal to the stress for the breaking, which is the 1 gigapascal, and solve for L. So we get L is equal to the breaking stress over rho G. And then we just put in 10 to the 9 pascals, put in the density, 7,800 kilogram per meter cubed, put in the gravity, 10 meters per second squared, and out comes an answer of 12,800 meters, or 12.8 kilometers, which is pretty good. You don't have to worry about steel cables suspended off of buildings breaking. This becomes a bigger issue if you're trying to do things like build orbital elevators and all kinds of other stuff. So you need things with higher breaking stress if you want to go to space for cheap. Until then, rocketry. See Unit 4. Anyways, moving onward, let's consider wiggly jello. In this case, we have a 5 centimeter cube of gelatin. So that means it's a cube with side length of 5 centimeters, resting on a table, 50-gram weight resting on top of it. Coefficient of static friction between the weight, this thing, and the gelatin, and between the gelatin and the table. So that surface and that surface have the same static friction of 0.7. And the shear modulus of gelatin is 3 kilopascals. A force F is applied to the weight. How far will the weight move before it starts to slip? So the free body diagram of the weight has a force that's pulled onto it. And if it's just sort of being gently pulled, it's going to be in equilibrium with a static friction force. And that static friction force is going to apply to the gelatin. So it's going to be applied to the top from the weight. And then there's a similar static friction force at the bottom. So there's going to be a static friction force here, Fs from the Earth. And then this is going to be Fs from the gelatin. And we're going to assume that those are the same, so the gelatin mass is negligible. And so then what we're going to do is consider, and then there's a normal force and an mg. So this sets up a shear problem, which means that we have our shear relationship, which says that the shear is equal to the shear stress, F parallel over A, times h over x, where h is how high up the cube is, and then x is what we want to find, which is how far it will move before it starts to slip. And then that parallel force is going to be in equilibrium. So there's a normal force from the gelatin, and then there's the weight of the gelatin pulling down, and of the weight pulling down. And so that maximum force before it starts to slip is going to have the form Fs is just going to be the static friction force times the mass of the weight times g, following everything we did in the forces unit. So from here, we can just solve for x. So x is equal to F parallel over A times h over the shear modulus. And then the F parallel is just going to be mu s mg times h all over A times s. And then we put in our numbers. So mu s is 0.7. The mass of the weight is 0.05 kilograms. The gravitational constant is 10 meters per second squared. The height of the gelatin is 0.05 meters. The area, the surface area, it's a cube, is just going to be 0.05 centimeters squared. And then the shear modulus is 3,000 pascals. And if we go ahead and work that out, the answer is 2.33 millimeters. Okay, so that gives us a little setup for a shear scenario. Let's consider this one. An ice cube, note cube, with side length of 3 centimeters is dropped into a glass of water. How much ice of the ice cube remains above the surface of the water once it comes to equilibrium? Okay, so we're envisioning a situation here where we have our glass of water, and then the ice cube is going to be in it here with some depth below the surface that I'm going to call y, and it's a cube with side length of L. And from here, I want to figure out what the forces are. We know it's going to be in equilibrium, so there'll be a buoyancy force pushing up, and that's going to balance the weight of the ice cube pushing down. So the weight of the ice, so the buoyancy force is just going to be the volume of the displaced water. So it's rho H2O times the volume that's displaced times g. So that's going to be the buoyancy force. And then M ice is going to be equal to the density of ice times its volume, which is the length cubed. And so then from here, we get these two are equal to each other. So we get that rho H2O times the volume below the surface, or the volume of displaced water, which is going to be L squared, that's the area, times y, which is the depth below the surface. So that's just the volume in this region there, times g is equal to rho ice times L cubed times g. And from here, we can solve for y. So we'll cancel out our g's. We'll cancel out L squared with L. And from here, we get that y is equal to rho ice over rho H2O times L. And so that's 920 kilogram per meter cubed over 1,000 kilogram per meter cubed times the length of this, which is 3 centimeters. And so that gives me an answer of 0. So that's 0.92 times 3 centimeters. And because I want the length that's above the water as the answer, so this is what we want. We want to find out what L minus y is. So that's 3 centimeters minus 0.92 times 3 centimeters. And that gives us 0.24 centimeters. So that's how much I should be sitting above your water when the ice cube comes to rest. Try it at home. Next case, a person pushes down on a hydraulic system with a force of 500 newtons on a surface with area 0.5 meters squared. If a weight is resting on the other end of the system, which has an area of 3 meters squared, what's the maximum weight that can be lifted at a constant speed? So this is basically just asking what the forces are. So we have that the pressures in a hydraulic system are the same. So the pressure there and there will be the same. So we know that F1, we'll call this F1 and that A1, and this will be A2, and so then that'll be F2. We know that F1 over A1 is going to be F2 over A2 in this scenario. So if we want to figure out the maximum weight, then we get F1 times A2 over A1 is equal to F2, and we plug in our numbers. So this is 500 newtons times the ratio of the areas, which is going to be A2 is 3 meters squared over 0.5 meters squared, and that's going to give us 3,000 newtons. So we get a mechanical advantage. Push down with 500 newtons, get a push up of the rate of the ratio of the areas, so 3,000 newtons pushing up. Interesting, fairly straightforward, but I want to ask, how far will the weight rise up if the force pushes the left piston down by 30 centimeters? And the key point here is it's going to rise up by some amount here. And the volume here, V1, is going to be the same as the volume that it rises up over here. So it's going to be, the volume there is V2. And so the volumes are going to be the same. V1 will be equal to V2. And in this case, I have that the cross-section, so that's area 1 times the length that it's pushed down, y1, and that is going to be equal to a2 times y2. So then if we're finding out what y2 is, why that's a1 over a2 times y1, plug in our numbers, 0.5 meters squared over 3 meters squared times 30 centimeters, and that gives me 5 centimeters. So the key point here is that I want to actually calculate the work that's done by these two forces, the force pushing down and the resulting force pushing up. And what happens in that case is I have F1 times the displacement, which was times S, which is my displacement, which was equal to 500 newtons times the distance it rises up, 0.3 meters. That gives me 150 joules. Cool. F2 times the displacement 2 is going to be the force that we've gained, 3,000 newtons, but it only goes up by 5 centimeters, or 0.05 meters, and that also gives me 150 joules. So even though we get a force magnification, just like in pulley systems, the displacements will be smaller. And since the displacements are smaller, we get an equal amount of work. So we don't get something for nothing using these hydraulic systems. Okay, final problem I want to work out is this case with a cylindrical tank of water. It has a height of 2 meters, a radius of 1 meter, so that's that, 1 meter. This is 2 meters. It's filled with water, and there's a tiny little hole with radius 2 centimeters at the bottom. How long will it take for the tank to drain? This is a Bernoulli problem, and it's kind of interesting because the pressure inside the fluids here is the atmospheric pressure. So there's an atmospheric pressure at the top, and then when the fluid comes out here, there's also an atmospheric pressure. And what we do is we kind of consider the flow at the top as one point. So this is one area that is flowing through. That's at some height h. It's going to become, I'm going to start calling it the height y, because y is going to change. And then the flow out at the bottom is also at atmospheric pressure because it's kind of vented to the air, but we can still apply the Bernoulli equation. So we're going to call the top here will be case 1, and the bottom here will be case 2. And what we have is that the pressure at 1 plus, using the Bernoulli equation, rho g, and we're going to work it out as y, the general height there, starts at h, goes to 0, plus 1/2 rho v1 squared is going to be equal to p2 plus rho g times 0, because it's at the bottom, of the tank there, plus 1/2 rho V2 squared. And we're going to have that P1 and P2 are equal, so that we'll cancel them out. The rho G0 is 0. And we're also going to assume that because the tank is so much wider than the hole, we're going to assume that the speed at the initial point in the flow is basically 0. So that last assumption, so we set V1 as approximately 0 because the flow is slow compared to speed of the water jet. Okay, so from here we have the things that we need. We have that, and then from here, so that gives me that rho gy is equal to 1/2 rho v squared, and then we can cancel out our rho's, and we get that v of the flow there, v, is equal to root 2gy. So it's basically the pressure is squirting it out at a speed root 2g times y. Okay, so that's how fast it exits through the hole. The volumetric flow rate through the hole is going to be equal to the volume that the rate at which the water level drops. So the volumetric flow rate through the hole is going to be A times the hole, A of the hole. Be very careful saying that variable. A of the hole times V2 is the volumetric flow rate. And I'm going to write that as pi times R whole squared times V2. And I know that that volumetric flow rate is the rate at which the volume leaves the tank. And so that's also equal to the chain. So we know dV by dt of the tank, of the water in the tank, is going to be equal to pi R whole squared times V2. Now the volume in the tank, d by dt, is just going to be pi times R tank squared times the height of the water. That's the volume there, and we're going to have the time derivative of that, and that's pi R squared of the whole times V2. Take the time derivative of that, pi R squared, constant, so we get dy dt, so it's pi R tank squared dy by dt is equal to pi R whole squared times V2, which we already know is 2gy. So we'll cancel out the pi's, and then we will end up with, I'm going to put the R, consolidate the r's, I get dy by dt is equal to R whole over R tank quantity squared, I'm shortening the variable names, times root 2gy. And that is a separable differential equation. So I'm going to divide under by the square root of y and multiply up by the dt. And that'll give me dy over square root of y is equal to RH over RT squared times root 2g. I actually need to be careful here because I've dropped one important consideration, which is that the flow rate goes down, the volume is actually decreasing. So I need to ad hoc insert a minus sign here to indicate that the volume of the tank is dropping based on how quickly water is flowing out there. It's in my notes. I just forgot to put it in here. So sorry about that. Want to make sure my minus signs are correct. Okay, because now, oops, I forgot my dt as well. Great. Now we have a fully cromulent differential equation that I'm going to integrate. I'm going to integrate the height from dy over root y from height y to 0. So it starts at height, starts at height h and it goes to 0. And then from there, that's going to be minus RH over R tank quantity squared times root 2g times dt, and that t integral is 0 to whatever time we're going to find out. What we want to find out. We do this integral, and so that's going to give, on the right side, we get that that's 2 times the square root of y evaluated from h to 0 is equal to minus RH over RT quantity squared times root 2g times the integral from 0 to, I can actually integrate that. I'm good that way. Times t minus 0. T minus 0. Okay. All right. So at this point, we have got our integral set up. We can evaluate the right side. So this becomes 2 times the square root of 0 minus 2 root h is equal to minus RH over RT quantity squared root 2g times t. And I want to solve for t. So that becomes 0. The negative signs cancel. See, I put it in there for a reason. And then I find that t is equal to, let's see here, 2 root h times RT over RH quantity squared divided by root 2g. And if we plug all this in, it's slightly neater to say root 2h over g times RT over RH quantity squared. And then we plug in our numbers. Square root 2 times 2 meters all over 10 meters per second squared times the radius of the tank, which was 1 meter, over the radius of the hole, which is 0.02 meters, quantity squared. All those numbers come in, and we get 1,580 seconds. So that's how long it takes to drain a tank. And we have to do the calculus because as the water flows down, there's not as much pressure forcing the water out. So the flow rate will decrease as time goes on. Okay. So that brings us to the end of our examples. I hope those were vaguely illuminating, and I will see you in class for further discussion.